Welcome back to Frequency Friday. We are going to talk about scalar waves today. Scalar waves are one of the most controversial and fascinating concepts in modern physics. They are a bridge between Tesla's visionary ideas and the cutting edge of the quantum field theory. Some researchers believe they could revolutionize wireless energy transmission and communication. Others dismiss them as pseudoscience. We're going to unpack some of that today. Today, we're diving deep into the scientific origins of scalar waves, exploring the evidence and the arguments and the ongoing mystery that has captivated researchers for over a century now. Before we get into the history, let's define what we're really talking about. So, what the heck are scalar waves? Scalar waves are theoretical electromagnetic oscillations that propagate along the direction of propagation longitudinally rather than perpendicular to it like conventional electromagnetic waves like sound waves, for example. In conventional physics, electromagnetic waves are transverse. The electric and magnetic fields oscillate at right angles to the direction of the wave that's traveling. But scalar waves oscillate parallel to their direction of travel. This is kind of strange. It's what kind of threw mathematicians off and James Clerk Maxwell when he was discovering these. This fundamental difference is at the very heart of this scalar wave controversy. If they exist, they would require entirely different detection methods and would represent a significant gap in our understanding of electromagnetism, basically throwing traditional physics on its head, which it does very well. Our story begins in the 60s with a Scottish physicist named James Clerk Maxwell. Maxwell was a super genius, one of the greatest minds in the history of physics. He unified electricity, magnetism, and light into a single elegant mathematical framework. This dude was way ahead of his time. But here's what most people don't know. Maxwell didn't write his equations in the form we learn in school today. Maxwell used a mathematical system called quaternions. Quaternions are a four-dimensional number system that extends complex numbers. I couldn't even describe it to you. I tried making sense of it, and this guy was just on another level. They're more general in nature than the three-dimensional vectors we use today, and crucially, Maxwell's original quaternion formulation allowed for both transverse and longitudinal wave components. This is important because in Maxwell's original mathematics, electromagnetic waves could potentially oscillate in the direction of propagation, which is just longitudinally and not perpendicular to it, like the transverse waves we know today. So enter Olivier Heaviside. Heaviside was an English engineer and mathematician who in the 1880s took Maxwell's quaternion equations and simplified them into vector form. Vectors are three-dimensional and much easier to work with mathematically. Heaviside's simplification made Maxwell's equations practical for engineers and scientists to use, and it worked brilliantly at first. Heaviside's vector formulation became the standard. It's what we teach in universities today. It's what powers all of modern electrical engineering, telecommunications, and our entire technological civilization. But here's where the controversy begins. Some researchers argue that in simplifying Maxwell's equations from quaternions to vectors, Heaviside removed or obscured certain mathematical terms, specifically scalar components. So it's kind of like a bastardization of what Maxwell originally did. Scientists suggest that longitudinal electromagnetic wave solutions became mathematically invisible. Mainstream physics, they now start to come in and disagree. They argue that scalar potentials are properly accounted for through something called gauge freedom. It's a mathematical principle that shows scalar components don't produce independent waves in free space. But scalar wave proponents maintain that Heaviside's simplification was a loss, not just a convenience. And the biggest reason for Heaviside changing up Maxwell's original calculations is because he deemed them too mystical. whatever that means, which means that he didn't understand it according to his level of physics. So what he did was he chopped it down and brought it down to his level of understanding, not Maxwell's. And then more physicists agreed because they understood that, and that's why it was adopted. To understand scalar waves, we need to understand scalar fields and scalar potentials. A scalar field is a concept from physics where a single numerical value is assigned to every point in space. Unlike vector fields or something like that, which have direction, scalar fields have only magnitude. Electrical potential, also called voltage, is a perfect example of a scalar field. Every point in space around an electrical charge has a specific potential value. This is real, measurable, scalar fields that physicists work with constantly. Now, scalar waves would be oscillations within these scalar potentials. Imagine the potential values fluctuating over time and space, creating wave-like patterns. In quantum field theory, scalar fields are fundamental. The Higgs field, which gives particles their mass, is a scalar field. The inflation field, theorized to have driven the expansion of the early universe, is a scalar field. So scalar fields aren't theoretical abstractions. They're real components of modern physics. The question is, can electromagnetic scalar potentials oscillate as waves in free space? And if so, why haven't we detected them? Well, we have mathematically, but what a lot of companies or physicists are doing is they're struggling to detect it via some type of machine. So to understand the scalar wave debate, we need to understand the fundamental difference between two types of waves, longitudinal and transverse waves. We're going to start with transverse waves. These are the waves you're probably most familiar with. In a transverse wave, the medium, or in the case of electromagnetic waves, the field, oscillates perpendicular to the direction of wave travels. Imagine a rope stretched between 2 points. If you grab one end and shake it up and down, you create a transverse wave. The rope moves up and down, but the wave itself travels horizontally along the rope. The oscillation is perpendicular to the direction of propagation, which just means the direction of wherever the waves are traveling. Electromagnetic waves are transverse waves. The electrical field oscillates up and down, the magnetic field oscillates left and right, and the wave travels forward. This is true for visible light, radio waves, microwaves, X-rays, all electromagnetic radiation. The transverse nature of electromagnetic waves is fundamental to how they interact with matter and how we detect them. Now let's talk about the longitudinal waves. Longitudinal waves are the medium oscillates parallel to the direction of wave travels. Think of a spring stretched between 2 points. If you push and pull on one end, you create a longitudinal wave. The spring compresses and expands. The wave travels along the spring's length. The oscillation is parallel to the direction of propagation, like we see right here. Sound waves are longitudinal waves. Air molecules compress and expand as sound travels through the air. The oscillation of the air molecules is parallel to the direction the sound wave travels. This is why sound can travel through solids, liquids, and gases, any medium where particles can compress and expand. Here's the crucial point for understanding scalar waves. Conventional electromagnetic theory predicts that electromagnetic waves in free space are purely transverse. The Maxwell Heaviside equations, which we talked about earlier, form the foundation of all electromagnetic theory, yet produce only transverse wave solutions when you solve them for waves propagating through empty space. There are no longitudinal electromagnetic wave solutions in the standard formulation. But scalar wave proponents argue that longitudinal electromagnetic waves should exist, that they emerge from the scalar potential components of electromagnetic fields. They claim that these longitudinal waves were mathematically present in Maxwell's original quaternion formulation, like I already talked about, but became invisible or they disappeared when Heaviside simplified the equations to vector form. The debate comes down to this. Can electromagnetic fields oscillate longitudinally like sound waves, or are they constrained to transverse oscillations? Mainstream physics says transverse only. Of course they do, but scalar wave researchers say longitudinal components should exist. This fundamental disagreement about the nature of electromagnetic waves is at the heart of the scalar wave controversy. If longitudinal electromagnetic waves exist, they would require entirely new detection methods and models. Standard electromagnetic instruments are designed to detect transverse waves only. They would be blind to longitudinal oscillations. This is why scalar wave proponents claim their waves are invisible to conventional detectors, not because they don't exist, but because we're looking for them with the wrong tools, like I explained earlier. Understanding this distinction between longitudinal and transverse waves is essential for evaluating scalar wave claims and everything we're going to talk about moving forward. The question isn't whether longitudinal waves can exist in nature. They clearly can, as sound demonstrates. The question is whether electromagnetic fields can oscillate longitudinally in free space. And that remains one of the most contested questions in physics today. So now we get to Tesla. My man, Tesla. While Maxwell and Heaviside were kind of working with equations, another genius in the form of Nikola Tesla was conducting experiments. If you're not familiar with him, Tesla was an inventor, an engineer with just extraordinary talent. In the 1890s and early 1900s, Tesla was conducting experiments with stuff like high voltage electrical systems that produced effects he couldn't explain with conventional electromagnetic theory. So Tesla starts taking his experiments into different realms and realizing, like, hey, stuff is going on that I really can't explain. And what he did was he started to call them non-Hertzian waves, waves that didn't follow the patterns discovered by Heinrich Hertz. Tesla believed that energy could propagate through space without losing strength over distance, defying the inverse square law that governs conventional electromagnetic radiation. He developed concepts he called radiant energy and conducted experiments at his famous Wardenclyffe facility in New York, where he attempted to transmit wireless power across several distances. Tesla's experiments with high voltage systems and Tesla coils produced unusual electrical effects. Discharge patterns suggested field compression and rarefaction, oscillations parallel to the direction of propagation, resembling longitudinal wave activity. So he's doing these experiments, and he's like, wait a minute, this stuff doesn't make any sense. It is turning out to be like scalar waves instead of sound wave activity. And as we all know, Tesla died penniless in a New York hotel. And when he passed away, there were several people from the government who came in and took all of his trunks and all of his notebooks and everything with him. And this is going to lead us into the second presentation that I'm going to do on scalar waves next week. Okay, but let's keep going. So when we are looking at this evidence, Tesla's most ambitious project was the Wardenclyffe Tower in New York that was constructed between 1901 and 1902. He believed that this facility could transmit wireless power to any location on Earth. The tower was designed to generate enormous electrical discharges that Tesla theorized would propagate through the ground and atmosphere as non-Hertzian waves. Some researchers reported apparent superluminal propagation in Tesla's experiments, suggesting energy transmission faster than conventional electromagnetic waves. So what we're going to learn in the second presentation is how scalar waves are not dependent or dictated by time. Okay. Tesla's work was super visionary in this respect, but it was also real controversial at the time, as you could imagine. His claims about wireless power transmission and non-Hertzian waves were never fully validated because, once again, Tesla worked alone, right? His Wardenclyffe project ran out of funding, unfortunately, and Tesla died in relative obscurity in 1943, his wireless power dreams unrealized. But his ideas never died. They lived on in the minds of researchers who believed Tesla had discovered something real, something that conventional physics had overlooked. According to scalar wave theory, these waves emerge from the interaction of electromagnetic fields in specific configurations. The theory proposes that when two electromagnetic waves of the same frequency are generated in opposing directions, they can interfere in a way that cancels out the transverse electromagnetic components while leaving the scalar potential component intact. This creates what proponents call a scalar wave, a pure oscillation of potential without the electromagnetic field radiation we normally associate with waves. The theory suggests that scalar waves can propagate through space and matter without the energy losses that affect conventional electromagnetic waves. They would be invisible to standard electromagnetic detectors because they don't produce the characteristic electromagnetic fields that our instruments are designed to measure. This theoretical framework connects Tesla's experimental observations to modern quantum field theory, suggesting that Tesla was detecting scalar wave phenomena that conventional physics hadn't yet recognized again. So this is coming around again and being like right in front of your face. Like, this is real. This is something that we know can happen, but the conventional physicists are like, because we don't understand it and we're the smartest people in the room, you don't get to play. Here's when we're looking at quantum theory, now people are starting to kind of catch on. And this is where modern physics gets a little bit more interesting. Because according to quantum field theory, the vacuum or empty space isn't actually empty. There's a great book by Lynn McTaggart called The Field that I would recommend everybody who's watching this. If you're really interested in it, if it's piquing your interest, go and check out Lynn McTaggart's work, The Field. And then she also has another great book called The Theory of Intention, which will just blow your mind. This is how I got into this stuff real early, man. I mean, I think I read The Field. I was still in college. So we're looking 1999, somewhere around 2000, something like that. So the vacuum is an empty space. It's not actually empty. It's filled with constantly fluctuating quantum fields. Particles continuously appear and disappear at subatomic scales, creating a dynamic energy landscape called vacuum fluctuations. Einstein even knew about this, okay? Even at absolute zero temperature, quantum systems retain residual energy from these field fluctuations. This is called zero-point energy. And here's the intriguing part. Tesla talked about extracting energy from the background field. His concept of radiant energy sounds remarkably similar to zero-point energy. This connection is one reason why contemporary researchers take scalar waves concepts seriously. If quantum field theory confirms that scalar wave fields are fundamental to reality, and if these fields can fluctuate, then perhaps Tesla's ideas about scalar waves have merit within a modern physics framework, and they're not so crazy. The question becomes, how do we detect and measure these phenomena? And that's where, again, the controversy deepens. Scalar fields aren't just theoretical constructs. They're fundamental to modern physics, like we discussed. The Higgs field is a scalar field. We know this. It permeates all of space and gives particles their mass. When the Higgs field has a non-zero value where everywhere in space, particles acquire mass. This was confirmed experimentally with the discovery of the Higgs boson at CERN in 2012. The inflation field, theorized to have driven the exponential expansion of the early universe, is also a scalar field. Temperature, like I mentioned, is a scalar field. Every point in a room has a specific temperature value. Gravitational potential is a scalar field. Every point in space has a specific gravitational potential. So scalar fields are real, measurable, and fundamental to physics. The question isn't whether scalar fields exist. They do. The question is whether electromagnetic scalar potentials can oscillate as independent waves in free space. And that's where mainstream physics and scalar wave proponents disagree. The regular scalar or the regular physicists get their panties all in a bunch and they get super, super frustrated. Despite a lot of these challenges, serious researchers continue to investigate scalar waves. One of the most prominent is Konstantin Mail. He's a German physicist who has dedicated decades to researching longitudinal electromagnetic waves. Mail claims to have replicated and detected scalar waves using modified Tesla coil apparatus and specialized measurement equipment. One of the devices that I have that has a Tesla coil in it is from Germany, actually. All the developers are from Germany. Mail argues that Tesla's ideas support the existence of longitudinal electric waves and that these waves can be described mathematically using Maxwell's original quaternion formulation. He's published numerous papers, holds patents on scalar wave technology, and has established research institutes to promote scalar wave research. However, Mail's work remains controversial, just as all this other stuff is when people don't understand it. His experimental claims have not been independently verified again or accepted by the broader scientific community, and his interpretations of Maxwell's mathematics are disputed by conventional electromagnetism experts. What's important to understand is that Mail is a serious scientist, not a charlatan. He's grappling with legitimate questions about the nature of electromagnetic fields and the completeness of Maxwell's equations. But his conclusions remain unproven. Why? Because there's levels to these games. A lot of these other physicists don't understand what Mail understands. Just like when I'm working with people on the table, I'll work on doctors, I'll work on physical therapists, I'll work on other massage therapists, I'll work on people doing cupping, I'll work on neurosurgeons, I'll work on ophthalmologists, okay? And they don't understand how I do what I do on the table. They don't understand it. Bro, that was amazing. I feel incredible. My pain is gone after 1, 2, 3 sessions. I have no clue how you did any of that. There's levels to this game. We need to understand. Another influential researcher that we have here is Thomas Bearden. He developed theoretical models of scalar interference. Bearden proposes that two scalar waves can cancel electromagnetically while still transmitting information and energy. And what we're going to learn in the second video next week is that scalar waves leave an imprint. They are all about imprinting information. But right now, this makes scalar waves invisible to conventional electromagnetic detectors. Bearden's work on vacuum energy and scalar wave suppression has influenced alternative science communities, though it remains outside mainstream physics. Again, like Mail, Bearden's theories lack experimental verification in peer-reviewed laboratories. What's important to understand is that these researchers are serious scientists, not charlatans. They're grappling with legitimate questions about the nature of electromagnetic fields and the completeness of Maxwell's equations, but their conclusions remain unproven. One of the biggest, most frustrating aspects of all of this. So when we look at scalar interferometry, what we are looking at, I want you to imagine for a second, if you could create a wave that carries energy and information through space, but it's completely invisible to every electromagnetic detector we have. Imagine this wave could pass through walls, penetrate the earth, and transmit power or data without any electromagnetic radiation signature. That's the promise of scalar interferometry, one of the most intriguing theoretical concepts in scalar wave research. So let me explain how this would work. First, let's recall what we know about wave interference. When two waves of the same frequency meet, they can either reinforce each other, creating a larger wave, or cancel each other out. I talked about this in my first video, okay, on authenticity. This is called constructive and destructive interference. You've probably seen this with water waves or sound waves. Two speakers that are playing the same tone at slightly different distances can create areas of loud sound and areas of silence, depending on whether the waves reinforce or cancel. Now, scalar wave theory takes this concept to a fascinating extreme. The theory proposes that if you generate two electromagnetic waves of identical frequency, but in opposite directions, one traveling north, one traveling south, they can interfere in a very specific way. The transverse electromagnetic components, the electric and the magnetic fields that oscillate perpendicular to the direction of travel, would cancel out completely. They would destructively interfere and eliminate each other. But here's where it gets kind of interesting, where I really like to get into. According to the scalar wave theory, the scalar potential components, the longitudinal components, would not cancel out. Instead, they would remain intact, creating what proponents call a scalar wave. This would be a pure oscillation of potential without any electromagnetic field radiation. The result would be an invisible information channel. Aha! Imprinting information. What did Chris talk about a little bit ago? So a wave that carries energy or data through space but produces no electromagnetic field that conventional detectors could measure. It would be completely undetectable by oscilloscopes, spectrum analyzers, or any standard electromagnetic instrument. You could have two scalar waves interfering with each other right in front of you, and you'd never know they were there. This is what baffles the scientists. This is why scalar wave proponents claim their technology is so revolutionary as well. They're not just talking about a new type of wave, they're talking about a completely new communication and energy transmission channel that exists parallel to the electromagnetic spectrum we know. The theoretical applications are staggering in this respect. Imagine secure military communication that's completely invisible to enemy detection. Imagine wireless power transmission that doesn't radiate electromagnetic energy and fry you like AirPods. Imagine medical devices that can deliver therapeutic frequencies without any electromagnetic exposure. But, and this is the big but, there are enormous practical challenges. First, generating scalar waves would require incredibly precise control. You'd need to generate two electromagnetic waves of absolutely identical frequency, amplitude, phase, and they need to be traveling in exact opposite directions. Any deviation would prevent the electromagnetic components from canceling perfectly. This is pretty technically and extremely difficult, all right? The second thing is you'd need to detect the scalar wave interference pattern. If the electromagnetic components cancel out, how do you know the scalar wave is there? You'd need specialized equipment designed specifically to measure scalar potential oscillations. This equipment doesn't exist in any standardized form, right now anyways. Third, there's the theoretical problem. Mainstream physics argues that gauge freedom, a mathematical principle in electromagnetism, means that scalar potentials don't produce independent waves in free space. Even if you could generate the interference pattern, it wouldn't propagate as a wave. It would dissipate almost immediately, just canceling everything out. Scalar wave proponents counter that gauge freedom is a mathematical artifact of the vector formulation and that scalar waves would propagate in the quaternion formulation of Maxwell's equations. But this all remains unproven. Despite these challenges, scalar interferometry captures the imagination of researchers and enthusiasts. It represents the possibility of a completely new physics, a hidden layer of reality that conventional science has overlooked. It also suggests that Tesla might have been tapping into something real when he conducted his experiments with high-voltage discharges. The question is scalar interferometry a genuine physical phenomenon waiting to be discovered, or is it a mathematical artifact that has no basis in reality? The answer requires rigorous experimental investigation. We need researchers with the skills, equipment, and funding to test these ideas properly. We need peer-reviewed publications and independent verification to shut these people up. We need reproducible results to shut these people up. Until that happens, scalar interferometry remains a fascinating theoretical concept that's intriguing, at least to me and maybe to you, enough to inspire continued research, but unproven enough that we can't claim it as established science, or can we? What we can say is this. The pursuit of understanding scalar interferometry drives innovation in measurement technology and field theory. Whether it ultimately proves real or remains theoretical, the question it raises about the nature of electromagnetic fields and the completeness of our current understanding are worth asking. And that's the essence of science: asking the right questions, demanding rigorous answers, and remaining open to possibilities while maintaining healthy skepticism. So I'm going to leave you off there. Okay. I hope you really enjoyed this presentation. And next week's is going to get a little bit nuts. I'm just going to put it out there. I hope you tune in, and I hope you have a great week. As always, Chris Kadowski signing off with love, light, and aloha.